Hello, this is the luckiest maths teacher in the world. Today we're looking at rationalizing the denominator. So what does that actually mean? Well, when we talk about denominator, we're talking about a fraction. So we have something on the top and something on the bottom, and remember the thing on the bottom is called the denominator. So rationalizing the denominator means we're going to take something with an irrational number in the denominator, let's say root 2, and we're going to make it rational. So luckily, you already know what a rational number is and what an irrational number is. Okay, so let's look at a quick example. So let's say we have the number 1 on root 2. So this is an irrational number. There's nothing at all wrong with this number or writing an answer like this. It's just that it's a bit hard to understand. In fact, if I asked a lot of people what 1 over root 2 is, they couldn't get it. It's not that they couldn't get it exactly right. They probably couldn't tell me about what it is. So we want to find a way to make this easier to represent. So what we're going to do is we are going to find an equivalent fraction. So we're not changing the number. And that equivalent fraction is going to have a rational denominator. So think back to year 7, taking you in a time machine again, when we looked at equivalent fractions. So if I have any fraction, let's say I have something on top like 2 on top and 3 on the bottom, for example, I can find any equivalent fraction by timesing or dividing both the numerator and denominator by the same number. So I could times the numerator and denominator by 2 and I get 4/6. 2/3 and 4/6 are the exact same number. If I divided a pizza into 3 parts and gave you 2 of those parts, exact same amount as if I divided the pizza into 6 parts and gave you 4. Okay? I could make this 40 over 60, for example, or I could then divide the top and bottom by, say, 4 and get 10 over 15. They are all the exact same number. They're all equal to 0.6 recurring. So what about 1 on root 2? Well, I can do the same thing to this fraction. It's just another fraction. The rules haven't changed. I can times or divide top and bottom by the same number without changing that number. What I want to do is I want to get rid of the square root on the bottom so that this becomes rational. So what I can do is I can times top and bottom by the square root of 2. So I'm timesing by root 2 over root 2. So essentially I'm timesing by 1. So remember, when you multiply fractions, you just multiply the top and multiply the bottom. So 1 times root 2 is root 2. Root 2 times root 2 is 2. Just like square root of 6 times square root of 6 equals 6, okay? So 1 on root 2 and root 2 on 2, they are the same number, but now you can see here the denominator is rational. 2 is an integer, a whole number, so it's rational. Now this just makes it a little bit easier to understand. See, a lot of people would know, and you probably know, the square root of 2 is about 1.4, so root 2 divided 2 is about 0.7. This is a lot easier for people to conceptualize and understand than, say, 1 on root 2. Okay? So we're just going to use this process on fractions today. So let's say I have 3 over the square root of 7. I want to make it rational. I just times by root 7 on root 7 because that will get rid of the surd on the bottom. So that will just become 3 root 7 on 7. As another example, let's say I have root 5 over root 8. So I'm not looking here to rationalize the numerator, just the denominator. So I'm going to times it by root 8 on root 8. So the top will still be, the numerator will be irrational, but the denominator won't be. So root 5 times root 8 is the square root of 40. Root 8 times root 8 is just 8. Okay, fantastic. So that's the easy part. But now we're going to look at when the bottom is a little more complicated. So if you want to copy this down, please go ahead because it's about to disappear. So before we explore cases where the denominator is a little bit more complicated, we're going to need to go through a rule that will come in handy, and that's the difference of 2 squares. So we actually learned this earlier in the year when we did an introduction to algebra. So if you have something that's a minus b times a plus b, if I were to go through and do the binomial expansion and all that, I'd end up with a squared minus b squared, right? So what does this have to do with surds? Well, the point is, if either a or b is a surd, we can use this result, multiplying it, to end up with something that's a squared or b squared, which gets rid of the surd, okay? So that might not make a lot of sense. So let's go through an example to elucidate this a bit more. So let's say I have 1 on, say, 2 plus the square root of 2, okay? Now the problem is, if I multiply top and bottom by root 2, on the top I end with root 2, but on the bottom, I'm timesing root 2 by the whole thing. So it won't actually become a rational number. This is root 2 on top, and if I expand the brackets on the bottom, root 2 times 2 gives me 2 root 2. And then root 2 times root 2 gives me 2. But this is not irrational, so I haven't rationalized the denominator. What I need to do is I need to multiply out like this. So if I have 1 on 2 plus root 2, what I need to do is multiply top and bottom by 2 minus the square root of 2, right? So notice here, I have 2 plus the square root of 2 and 2 minus the square root of 2. So this is like a plus b, and this is a minus b. So what's going to end up happening, as we saw at the top here, is that we're going to square the a and square the b. So that will get rid of the square root. So let's do this. So on top, 1 times 2 minus root 2 is just 2 minus root 2. Now on the bottom, I have 2 plus root 2 times 2 minus root 2. So using the difference of two squares, my top's still the same. I just take the first one and square it, minus the second one, and I square it. So on top remains 2 minus root 2, but on the bottom I get 2 squared is 4 minus root 2 squared is 2. So of course 4 minus 2 is just 2. I can rewrite that as 2. Now it does have a rational denominator. So I've used the difference of two squares. So let's go through a few more examples. So let's say I have something like 3 over root 5 minus 4. So what I do is I multiply top and bottom by the denominator, but instead of the minus, I change it to a plus. So I'm going to multiply top and bottom by root 5 plus 4. Okay? So on top, I'm going to get, remember this is an expansion, I have to multiply the 3 by root 5. Then I have to multiply the 3 by 4, and my top's done. On the bottom, because this is the difference of two squares, a minus b, a plus b, I just square the first, so root 5 squared is 5, and then I square the second term, which is 16, and a minus goes between them. So this becomes 3 root 5 plus 12 over minus 11. So the bottom number is now rationalized. Let's say I have 8 over square root of 2 plus the square root of 3. The same process follows. I want to multiply top and bottom by the denominator of this fraction, but I want to change the sign. I want to change the plus now to a minus, so I can use the difference of two squares law that I showed you before. So I'm going to times top and bottom by root 2 minus root 3. Okay, so again, we have to multiply this number on top by everything on the top of the second fraction. So 8 times root 2 gives me 8 root 2. 8 times negative root 3 gives me negative 8 root 3. So that's the top done. And the bottom, square the first. So root 2 squared is 2. And then square the second. Root 3 squared is 3. And then a minus between them. And I can rewrite this 2 minus 3 as negative 1. Okay? Now this has a rational denominator. I can clear this up by timesing top and bottom again by negative 1, and it'll become 8 root 3 minus 8 root 2 over 1. Or I don't need to even write that. Okay, so when rationalizing the denominator, times the top and the bottom of the fraction by the conjugate of what is on the bottom, just like I have done here. It's just the same as finding equivalent fractions like you did in year 7, only we're using the difference of two squares law. Hope you've found this video useful. This has been the luckiest maths teacher in the world. Have a great day.